Lesson 5.1, use properties of exponents. Now, properties of exponents are found when you have different bases and different exponents, and there are ways to simplify. In this term, a to the b, the a stands for the base of your term, and the b value represents the exponent of the base or power. Those terms are used kind of interchangeably. Let's take a look at these several properties down below. Our first property is product of powers. Product meaning you're multiplying the bases, and then we'll figure out how we simplify the powers. When you multiply bases that are the same, you actually add the exponents together. And that's how you would condense it down to just one base. That's simplifying with a product of powers. Our next property is power of a power. And this, notice we have an exponent on the inside and the outside. If you have one base but an exponent on the inside and the outside, a way to simplify this expression is to multiply. So m times n. It's like giving a superpower when there's a power on the inside and the outside. We multiply to make it bigger. Next, we have power of a product. Now notice there's only one exponent, but in the parentheses, there's a product of things happening. It says AB in the parentheses to the m power. If an exponent is on the outside of a parenthesis and there's a product on the inside, notice it's not addition, but it's a times b. That means each unique base on the inside will get that exponent. So that means a to the m power times b to the m power. So remember, this doesn't work for addition, and we've talked about that quite a bit this year. Moving along to a negative exponent. Anytime a base has a negative exponent, to simplify, you want to make your exponent positive by taking the reciprocal of the base. So watch what happens here. If we have a to the negative m power, that would be the same as 1 over a to the positive m power. And this will be true as long as a isn't 0. Because if a were 0, we can't have 0 in the denominator. But watch also what would happen if you have a fraction to a negative exponent. So maybe you have a over b to the negative m power. Well, if you have a fraction to a negative exponent and you take the whoops, I don't know why that's fuzzy there, and you take the reciprocal of the base, when you take the reciprocal of the fraction, that would just change b over a, and then your exponent would become positive. The next property is so simple, and it's one of the ones that's commonly missed because it is so simple. The zero exponent property. Any base raised to a power of 0 always equals 1. It's very simple. Even if you had something like a product of, or a power of a product, AB to the 0 power. No matter what that base is on the inside, oops, that's supposed to be a 0, sorry, let's fix that quick. If you have 0 as an exponent, maybe, there we go, it automatically equals 1. So just recognize anytime that exponent is 0, you automatically know your answer. We've done a lot of work with products. Now let's take a look at a couple of quotient definitions. Quotient of powers is very similar to product of powers, except instead of multiplying the base that's the same, we're dividing. So to work with our exponents, we're going to do the opposite as well. Instead of adding our exponents together, we're going to subtract them. And order matters when we subtract. It's always the top exponent minus the bottom exponent. And that will allow you to simplify and condense this down to one base. And then our final property, power of a quotient, is kind of like power of a product. If you have a quotient and you have it in parentheses with an exponent, as long as there's no addition or subtraction, you can distribute that exponent to the numerator and denominator of the fraction. This would give you a to the m power over b to the m power. Now we're going to be able to utilize these properties with bases that are numbers and bases that are variables. And here's our plan. We'll evaluate a number base, which means once we simplify it down to one base, we can evaluate the exponent by multiplying. And then we'll simplify anything with a variable. We won't be able to evaluate a variable base because we don't know what that value actually equals. Let's take a look at several examples down below. To start off, let's evaluate each expression in A through E. It says keep answers in fraction form, no decimals. So if we have to have a fraction answer, we'll keep it just like that. We won't plug it in and try to get a decimal approximation. Our first example, we're going to take 6 squared times 6 to the negative 5th. Notice our bases are the same and we're multiplying. So this is called product of powers. To condense this expression down to one base, we're going to add the exponents together. So that would be 2 plus negative 5. And 2 plus negative 5 would be 6 to the negative 3 power. That condenses our base down to 1, but now we have a negative exponent. And the rule for negative exponents is we take the reciprocal of the base. 6 then becomes 1 over 6, and the exponent drops down with the 6 and becomes positive 3. So now to evaluate, the 3 doesn't stay with the numerator, so we're just going to have 1 on top. 6 to the 3rd power, well 6 times 6 is 36, and 36 times 6 is 216. This would be the simplified final answer for that product. Example B. We have a fraction now to the negative 3rd power. So again, we've got that negative exponent, but we also now have power of a quotient, where the top and the bottom of the fraction are going to get the exponent on the outside. But I'm going to take the reciprocal of the base first to make my exponent positive. So instead of 5 halves, I'm going to have 2 fifths. And then that makes the negative 3 become positive 3. Once it's positive, I'll distribute it to the top and to the bottom. And that would give us 2 to the 3rd power over 5 to the 3rd power. Since these are number bases, we'll evaluate 2 times 2 times 2 is 8. And 5 times 5 times 5 is 125. And that fraction is simplified. It doesn't reduce down to 2 fifths. So 8 over 125 would be our final answer. Next up, we have 7 to the negative 3rd on the inside, and then on the outside, it's being squared. This is known as power of a power. If you have just one base already, but an exponent on the inside and the outside, we combine this pair by multiplying. It's like we give 7 a superpower. Negative 3 times 2 would be 7 to the negative 6 power. It's still a negative exponent, so then what that means is we take the reciprocal of the base. And the exponent moves down with the 7 to be positive 6. To evaluate that, 7 to the 6th power, so 7 times itself 6 times, is 117,649. And that would be the simplified fraction answer. If you have multiple bases that are the same, 2 to the 6th power times 2 to the 0 power times 2 to the negative 5th power, we can condense that down to one base by adding all of the exponents together. That's the product of powers property. 6 plus 0 plus negative 5. Well, 6 plus 0 is 6, plus negative 5 would just be 2 to the 1st power, and that's just 2. So that one ended up not being a fraction answer. Last but not least, we have another power of a power example. 3 squared on the inside to the 0 power on the outside. Well, 3 squared on the inside would be 9, and 9 to the 0 power would automatically be 1. You could also think about it with that power of a power. 2 times 0 is 0, and then 3 to the 0 power also equals 1. So again, anytime you recognize a 0 as part of your exponent, look what your answer was in either form. It just automatically equals 1. Now, you don't have to write it technically twice. As long as you get to 1 using either method, you're in great shape. For F through I. Simplify each expression, keep answers in fraction form. Again, no decimals. When we incorporate variable bases, all we can do is apply the properties. Once you've condensed that property and simplified it completely, there's nothing else we can do to evaluate. In our first example, F, we have b to the third power, b to the eighth power, b to the negative 4 power. Since all three of them are just right next to each other, it's a product. This is an example of product of powers. If all your bases are the same, we can simplify our exponents by adding them together. That condenses our base down to 1. 3 plus 8 minus 4, well, 3 plus 8 is 11. 11 minus 4 is 7. And that would give us b to the 7th power. And that's all you do. However, sometimes you could have a number mixed in with your variable bases. Let's take a look at example G. We have several properties being applied here. Inside the parenthesis, we have a 3, we have m squared, and we have n. That's 3 different bases, 1 number base and 2 variable bases. Because it's in a parenthesis and there's an exponent on the outside, this is an example of power of a product. Since nothing's being added or subtracted, the 4 goes to the number base, the exponent that's already there, and the base at the very end. So this kind of splits it up into 3 different parts. 3 to the 4th power times m squared to the 4th power times n to the 4th power. Now remember I said we couldn't simplify or evaluate with a number or variable base, but notice right here we have a number base. 3 to the 4th power. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So that number out in front, instead of being a 3, actually changes up to 81. And then m squared to the 4th power. This is power of a power. One base with an exponent on the inside and outside of the parenthesis. We multiply. M gets an exponent of 8. 2 times 4. N to the 4th power, well, guess what? Nothing else we can do with that one. Therefore, our product is 81, m to the 8th, and n to the 4th. Example H has a quotient, r over 5 to the 3rd power. So this would be the power of a quotient rule. R and 5, it's a division problem, so there's no addition or subtraction. That means that we can distribute the 3 to the top and bottom of that fraction, giving us r to the 3rd power over 5 to the 3rd power. If you look at this fraction, think about, is it simplified completely? Well, the numerator is, so if you thought r to the 3rd power was good, it is. But now 5 is a number base, not a variable base. 5 to the 3rd power, we already did that one up above. That would be 125. That is your final answer for that fraction. And we saved the best for last. Let's take a look at example I. There's a lot happening here as well. I see we have x's and y's in the numerator and denominator. We also have a parenthesis, and then I see a negative exponent. There's a lot happening here. Well, if we think about order of operations, anything with a parenthesis should typically be evaluated first. So let's take a look at this numerator right here. X to the negative 3, y to the 3 being squared. There's 2 different bases, so that's power of a product. We're going to distribute the 2 to both of those powers to give them a superpower, and then that cancels out the parenthesis. So we're doing a combination of power of a product and power of a power. Now, if we take x to the negative 3 and we square that, negative 3 times 2 would be x to the negative 6th power. Y to the 3rd raised to the 2nd power, 3 times 2 is positive 6. And that eliminates the parenthesis if we distribute that exponent in. Now, in the denominator, we've got x to the 5th and y to the 6th. If we take a look at the quotient of powers rule, we can kind of break apart matching bases. X to the negative 6th over x to the 5th, you can condense that down to one base by subtracting. Negative 6 minus 5. And then the y's, we can kind of do that same property too. y to the 6 minus 6. Well, if we simplify, negative 6 minus 5 is x to the negative 11, while y to the 6 minus 6 is 0. If you have a negative exponent, we have to take the reciprocal of x. So that's going to put us at 1 over x to the 11th. And what do we remember about y to the 0 power? Y to the 0 power just equals 1. So if we multiply 1 times 1 in the numerator, that doesn't change anything. It's just 1 over x to the 11th power. And that's your video lesson for 5.1. Your CYU assignment for 5.1, 1 through 14 all and 24 through 36 all. Take your time and make sure to use your property of exponent definitions up above.